All right, let's bring this all back down to earth for a second. Because if you go and try to run one of these massive, world-changing algorithms today, you are going to hit a massive brick wall.
As anyone following the space knows, we are squarely stuck in what physicist John Preskill famously dubbed the NISQ era back in 2018, noisy intermediate scale quantum. Basically, we have enough physical qubits right now, say 50 to a few hundred, to be genuinely interesting. But because we don't yet have robust quantum error correction, these incredibly fragile systems are still severely hampered by environmental noise and decoherence.
There is a brutal noise floor penalty we're dealing with, largely created by limited connectivity in a lot of these physical layouts. It strictly limits how many sequential operations, or gates, we can successfully perform before the whole system just collapses and spits out garbage data. We can add all the physical qubits we want, but if that noise floor stays too high, the effective depth of the math we can actually do remains frustratingly shallow. Let's put the real impact of that noise into perspective. Imagine you run a pretty basic 100-step circuit on a system today that boasts a 99% gate fidelity. 99% sounds amazing, right? Almost perfect. But here's the catch. Because every single gate introduces a tiny, microscopic fraction of an error, compounding over those 100 steps, your final output only has a 37% chance of actually being correct. Truly useful algorithms, like the ones needed for complex chemistry, require millions of gates. Without error correction, the true signal completely drowns in the noise before the algorithm even finishes running. So as we grind our way through this crucible of the NISQ era, we're really left wondering what the actual timeline looks like. The foundation for a massive new quantum economy is literally being built as we speak, one incredibly fragile qubit at a time. But the billion-dollar question remains. Are recent breakthroughs going to finally bring us to the promised land of fault-tolerant, error-corrected qubits in the next 5 years? Or are we staring down the barrel of a long, cold quantum winter? What do you think?